Hi, my best chemistry students. We're in the midst of talking about the factors that affect the rate of a chemical reaction. Now, the last factor is one we're actually going to land on for a while, and that is concentration. Actually, one of my favorite games when I was a little girl was concentration. Okay, very different concentration though. Now, this is in terms of the reactants only. Now, in real life, products can show up, but we're not going to be seeing that at all. For now, we're introducing it as the effect that varying reactants can have on the rate of a reaction. And we're only going to be using molarity. So we're going to discuss this in terms of moles per liter. So in a rate reaction, A plus B, if there's a low concentration, there's few collisions. If there's a high concentration, there's more collisions. It's analogous to what happens when you increase the pressure on gas phase reactions. You get more molecules per volume, you're going to have more collisions. More collisions means greater likelihood that those collisions will be effective to go on to make product. Now, what we're going to find that when we have an overall reaction, it's possible that one or more affect the rate. Now, since A going to B might happen in multiple steps, you know, A plus B going to AB, what can be unusual is finding that it might not depend on both of these, but it possibly could. So we're going to start with the possible reactants. Okay? I know that's a little tricky, but bear with me, and I think in the end, it's all going to fall into place. All right? Now, what we do in here is, and we're going to get more into the exact amounts of this, but if A doubles and the rate doubles, okay, if B doubles and the rate doubles, that would mean it's a one-to-one relationship. If B doubles and the rate quadruples, we have a squared relationship, and that's what we want to delve into in a later unit. In general, an increase in the concentration of one or both or all, if there's more, reactants generally increases the rate. Okay? Now, just how much, we're not sure. We're going to define that impact by a term called the order of a reaction. And that order of a reaction cannot be obtained by the overall stoichiometry, because that order comes from the steps that are involved. The overall just says, hey, I looked at it at the beginning, it had A plus B, I checked it at the end, and A and B were together. It doesn't say the pathway. So A meets B and falls in love and gets married. And somebody says, wow, A and B were single, now A and B are married. But what the person doesn't see is the pathway, the dates, the relationships, the squabbles, and so forth that led them to that final state. Okay? Instead, we have to determine this by looking at experimental data. So we're going to be looking at experimental data to determine the rate or the order or the impact. Okay? So hopefully that helps. Let's do a quick summary here of our 5 factors, and then we're going to zero in the next video on concentration. So, type of reaction, double reactions, typically we're making generalizations, but typically they happen very, very fast. Single replacement synthesis, decomp occur more slowly because elements change oxidation number. and these are called redox reactions. Now, there are exceptions. Combustion's a redox reaction, and combustions tend to happen pretty quickly. But as a general guideline, if electrons need to be exchanged, it's going to be typically slower. Temperature increases the reaction rate. Increase in temperature means we have an increase in kinetic energy, which is going to be increase in the energy of our collision. And that in turn is going to increase our reaction rate. Pressure, an increase in pressure will increase a reaction rate due to increased collisions, but it only has an impact on gases. I mean, put a pressure on a liquid. It really doesn't compress a liquid very much, and certainly a solid is imperceptible at normal room temperatures. An increase in surface area, and be careful, a few kiddos get a little bit confused by this. An increase in surface area means we're talking about smaller pieces, because if you chop it up, there's more surface showing, and that's going to increase the reaction rate. Adding a catalyst will increase the reaction rate because it provides an alternative pathway, and that alternative pathway lowers the activation energy, that barrier in the reaction. And then concentration and increase in concentrations will increase. Not all of them will increase, but at least one of them will increase, will increase the reaction rate. So increasing the concentration of one or more, it could just be one of the reactants that have the key effect, and we'll see that later. That gets more complicated. But as a generalization, you increase the concentration, you will generally increase the reaction rate. For example, if I go from 1 molar HCl, fairly dilute, relative to 6 molar HCl in a reaction, the rate's going to be higher with the 6 molar HCl. Okay, let's move on in the next to talking about concentration effects in more detail. Until then, this is your best chemistry teacher signing off.